Hello and welcome to my presentation about the transformer-based light fusion mechanism for fine-grained object recognition in videos. My name is Stefan Wolf and this work was done in cooperation with Yannick Koch and Jürgen Beirer. First on, what is fine-grained classification? So while in coarse-grained usual classification, we distinguish cars from, for example, humans or birds. In fine-grained classification, we focus on a single class, for example, cars. And inside of this class, we have different new classes. So here in this example, we have two classes. Both are Audius However, they are only distinguished by their year. And still, they um, are two different classes while sharing most of their visual appearance. So for what is this useful? Here I have two example applications. First on in surveillance, mostly, or it's really common to search suspects based on their car. However, criminals tend to use stolen license plates, so they can't be identified anymore by their license plate. So it's useful to be able to classify cars according to the model, so we can still find criminals based on their car model. Another application is in biology, where it's useful to classify plants so we can know whether it's a poisonous plant or not. Why should we use videos for this task? So, like I've said, we really have to focus on fine visual differences to distinguish cars. And here it's useful to have as many features as possible for the classification. And there, videos provides us different views of a car. So we can see the car, for example, from the front and from the back. So we have a much larger variety in terms of features available. Another aspect is that a single image might contain inappropriate frames like the one in the lower left, which shows heavy motion blur. In videos, this can be compensated by using other images. So what have been done in this field yet? So previous work in terms of video classification is mainly focused on action recognition. This means they put a high emphasis on extracting short-term context, so to extract the motion, for example, of humans. And they do this with early fusion architectures because they apply really dense sampling of images. So images have only small differences and they can be interrelated early in the classification architectures. So two recent examples of such architectures are video swing transformers and the video vision transformer. However, as we will see, this is inappropriate for fine-grained object recognition in videos, since here we want to have different views and extract long-term context of a video. On the other side, in terms of the fine-grained object recognition, the research is mostly focused on single images. However, here we see that the models are converging to usual deep learning based classification architectures recently. However, exploiting videos is rarely considered in this context, so there aren't really recent state-of-the-art architectures for this task. Thus, we started off with building a baseline by using a recent single image classification architecture and combining it with a averaging of the results. This is the Swin transformer, we call it here. And we evaluate it with two different sampling strategies. The first is a sparse sampling strategy, where we spread out the extraction of the images over the whole video to get a wide variety of views. The dense sampling is usually applied by recent architectures where a single clip is extracted. So while this clip only covers a short snippet of a video, it has a high frame rate while extracting. So when we look at the results, we clearly see the advantage of the sparse sampling, which provides a high variety of views. Then we also tried out Video Swin Transformer as a recent state-of-the-art architecture. However, we saw that the sparse sampling wasn't working out well at all. So this makes sense since the Video Swin Transformer is an early fusion architecture and it relies on small differences between consecutive images. So it doesn't need to extract semantically high features before it can start with an interrelation of the images. So what can we take away from this? So first, we need a sparse sampling strategy, and the second is we need a late fusion architecture to perform well in fine-grained object recognition. With this in mind, we designed a new architecture, the transformer-based late fusion mechanism. So we start with a sparse random sampling where we divide the video into segments and extract a single frame from each segment. Afterwards, we apply a recent state-of-the-art Swin transformer network for the feature extraction. So we have a feature vector for each image. All these feature vectors we are feeding into a transformer encoder layer that provides us a sophisticated interrelation of the features. And afterwards, we are averaging all outcoming feature vectors. So we have a single resulting feature vector that we put into a classification layer. Looking at the results of our new architecture, we see that it provides a real high accuracy compared to as well as baseline models like the Swin transformer with a simple average fusion, as well as compared to recent state-of-the-art video classification architectures like the Video Swin transformer or the Timesformer. It does this while also keeping the efficiency high, so we only have a small increase in terms of computational complexity and parameters. So to conclude the presentation, overall the dense sampling isn't really appropriate for fine-grained object recognition in videos. So we have seen that the sparse sampling is performing a lot better, particularly with using a late fusion architecture. So based on these findings, we designed a new transformer-based late fusion mechanism that provides a sophisticated fusion and thus heavily improves the accuracy and also increases the efficiency of the networks. With this, I'm at the end of my presentation and thank you for your attention.